Yeah, I know.
So, so the other part of infiltration is, and the more interesting part is capillary pressure. And so when you have negative voids in the soil matrix, you get a negative pressure that pulls the water into the soil. And so it's like if you stick a really thin straw into a glass of water, the water will go up into the straw because it pulls it up in there. So in a rainfall event, the soils near the surface, they become wet or saturated. And then the drier soils beneath continue to exert suction on the water, resulting in a continued downward movement. So types of porous media flow or capillary driven, that's that pressure, that negative pressure in the soils or pressure differential in the soil. Gravity driven, which is the water being pulled down, which can give you these preferential flow patterns like we saw in the cool picture in the other presentation that I don't have anymore. And then macropores are like things like roots that have from a dead tree, or like worms dig holes in the ground and the water flows down through those macropores. And the flow is actually not Darcy flow anymore. It's actually like a laminar or even turbulent flow if the hole's big enough. Oops, I don't do that. Do this. So in the GSSHA model, there's a lot of different infiltration options, and that's kind of the case for most of the processes in GSSHA. And so we have is there a problem then? We have the Richards equation, which is numerical solution of flow equations through a layered system. We have the Green and Amp, which is a simplification of the soil column and flow equations, no layering, and what's called a piston flow because there's a completely sharp wetting front. There's multiple layer Green and Amp model, which is just the basic Green and Amp model through a multi-layered soil column. And then there's a Green and Amp redistribution, which is the same Green and Amp model with the repetition of soil column with redistribution of soil moisture during rainfall hiatus, meaning between rainfall periods. So these are representations of infiltration in the soil. So on the left-hand side of the screen this is the soil moisture profile. So it'd be saturated at the groundwater, it'd be saturated at the top during infiltration. And then you have a wetting front, and then you have some old wetting fronts from old storm events. And then this picture, this convoluted looking picture, is the result of this not being a presentation, but it demonstrates the different soil moisture fronts represented in a Green and Amp model with redistribution. And so if the sharp wetting front comes in, it over the depth of that it gets on the previous event, then it's redistributed and you get a new initial soil moisture for your next rainfall event. I know that's hard to see. So effects of soil moisture on capillary pressure. So the soil moisture has a big effect on what is the capillary pressure in the soil. And so drier soils have, higher negative pressures. So these are graphs of different soils and different models. Why that thing keeps popping up? I know I'm sharing my screen. And so the thing that's kind of interesting is the soils are there's orders of magnitude involved in the pressures, and so wet soils. Wet soils, are down. It's wet soils. The pressure here is very low, but it is in a dry soil. The pressures can get very high. I mean, when I say high, I mean very low because these are negative pressures. And this would be like a sand. It has looser soils can't get as low a pressure as like a tight soil, like a clay. And these are clay curves, and they're 2 orders of magnitude higher negative pressure. that doesn't work. I keep forgetting. And so this is the curve of infiltration into a sand over time. And infiltration starts out, the infiltration rate, which is how much water is going in per unit of time. And so it starts out very high, but as the soil wets up, it approaches asymptotically the saturated hydraulic conductivity. They're talking, it's very hard. This is pretty tough. Factors that affect infiltration are the soil texture, the initial soil moisture, soil layering, the vegetation on top of the soil, macropores, and the location of the water table. There. I can't see my screen because it keeps telling me I'm sharing. Soil moisture during the infiltration. So here's a representation of a soil column, and you've probably seen these. You get the different horizons, ABC horizons, and then the stuff below it, just kind of called the groundwater media. And then at a static, or this is during infiltration, you have wet coming in, and that you get a wetting front, and then this would be like your initial soil moisture that you had, and then you always get this kind of curve from the groundwater to the surface if there's nothing moving down there. This is a mathematical description of the continuity equation. So the Richards equation is a combination of the continuity equation and the Buckingham-Darcy law. And so the continuity equation, it's the same continuity equation we saw yesterday for flow, but in this case, we're using, water content instead of depth, and that's really the only difference. And then this is the direction here is vertical, so we're talking about a one-dimensional vertical description. This is the Buckingham-Darcy flux law, which is the other part of the Richards equation, and it describes the flow. And the two important things is that the hydraulic conductivity, as we talked about, is dependent on the psi, which psi is the soil moisture pressure. And then here's your gravity term over here, the change versus z of this one and this one. And so the gravity term would be this, and then this is called, I forget when you do this, it's called C, but I don't remember the off the top of my son. Yeah, but when this term,
What's it?
d psi dz is, it has a name. Oh, it's this one, the specific moisture capacity. So this term is this horrible thing, and then the only thing I'm going to say about it is it's extremely nonlinear, and so it makes a mess. So you have very nonlinear coefficients in Richards equation. So if you look at this capillary, this is this term, this specific soil capacity, as it varies over saturation. You can see these nonlinear curves, and then we saw this log of permeability. Permeability is a term for hydraulic conductivity for any fluid, basically, not just water. And then you see these vary. This is a log, right? So these vary 12 orders of magnitude over the like wetting front from 0 to 1 soil moisture. So that's extremely nonlinear. And so Richards equation is because of these nonlinearity of the parameters that go in it, it's kind of hard to solve and it's time consuming. And so usually in hydrology we use Green models to simplify the equations. And so we do that by saying, well, the front is sharp, infiltration is unlimited, the soils don't vary, the initial moisture is uniform, and there's no effect of the water table. Okay, we don't have time.
Oh.
Sorry. No.
Who's the next equation?
Yeah.
In 2010, 2000, or 2000, or around the 2000s, there's an analytical solution developed for this equation. This Gaussian equation is essentially similar to the Richards equation. they both used to have to be solved numerically, but now Goosenet's equation does not have to be solved like it's an analytical solution. So I was wondering, have you thought of like changing it to make this computation simpler, just to put an analytical solution in there without having to do it?
I'm not.
Oh, okay. The problem came out right when this model was being finished, developed, the GSSHA model. So that's what I'm saying. It's pretty new.
Yeah. I mean, to me, the Booz-Next equations are using saturated groundwater media. I'm not aware of an application in saturated.
It's supposed to work in unsaturated too. But
I'm not familiar. So I just have to say I'm sorry. So I don't know. All right. Okay, back to this thing. Okay, so this is our green and amp model of infiltration, where we have an initial moisture, we have a saturated piston moving, and it moves down like that. So that's, compared to the Richards equation one, which looks like that. So you can see it's pretty simplified. But the beauty of it is it's easy to solve. We assume that the hydraulic conductivity of the wetting front is a constant value. We're talking about the hydraulic conductivity right here, and we already showed back here that it varies 12 orders of magnitude over the soil moisture profile. So we're going to assume that it varies none. And and then the capillary effect can be expressed as an effective wetting front suction head. And so that pressure at this front right there that's pulling it down, it's this, and it's always this. So those are the assumptions that get you to the green and amp equation. And so the nice thing about green and amp is it's a simple algebraic equation that's solved iteratively, the Newton-Raphson technique, very simple, very fast. That's the cumulative infiltration. This is the infiltration rate. And the green and amp parameters that you need to specify in your model are this wetting front suction head, the effective porosity. Effective porosity is the total porosity minus the porosity that you can't get out without cooking it, the residual porosity. The effective hydraulic conductivity is equal to Ksat over 2. And that's important. Everybody gets this. Everybody, even experienced modelers, forget and put saturated hydraulic conductivity in there. And then an initial water content. So to put in your green and amp parameters, they're derived from the soil texture map, or a combination of soil texture and land use. The land use can affect the soil texture properties by breaking down the soil matrix. Like if you plow it or drive on it or various unsundered activities, you can change the soil matrix, and you change the properties of the soil. So this is assigned with our mapping table, like we talked about yesterday. And initial values are taken as average values from Rawls et al. Rawls et al. They went out into the world and collected samples for 100 years and thousands of samples, and they've published these values of parameters in the ranges. So it's really nice. They also get the soil texture from Saxon and Rawls. This is just a building. This is a building on their previous work. And then your calibrated values are constrained within the limits of these publications. And so this is just what you can get from Saxon and Rawls. The different the soil hydraulic properties are derived from the texture, the organic matter, and the structure. The organic matter can affect your different soil parameters, because your standard computation of hydraulic conductivity and stuff is based on sand, silt, and clay, not organic matter. This is from a statistical analysis of measured data. Like I said, they're big field guys, or they were. I don't think either one of them are still practicing anymore. So there's a paper and spreadsheet in your materials. They have that. No, okay, there's not, never mind. The green and amp is valid for the following conditions: Hortonian runoff. That's the infiltration excess. If you remember my very first talk. So that's high intensity rainfall. It's fine textured soils. It's arid to semi-arid regions. Deep homogeneous soils. If we have layered soils, we can switch over to the layered model and kind of get around that assumption. And the water table being far from the soil surface, once again, we can couple our green and amp solution to our saturated groundwater model and get around that assumption. We can't get around this assumption, but you will find in the literature and in the world and in practice that people use green and amp for everything.